To help understanding lectures, we provide to you several complementary materials. In this complementary material, I am going to introduce you into the tensors. So we will use English proverb, keep task small. So to study tensors, we will consider two-dimensional tensors, which is much simpler, and most of the expressions, intermediate expressions, can be written explicitly. So we will consider flat space two-dimensional tensors. To introduce you into what means tensors, let me start with a vector. All of you know what means vector. Vector is, in two dimensions, is something which carries two components. But there is a distinction between a row of numbers and a vector. Vector is some quantity which appropriately transforms under the coordinate transformations. Namely, if we have a vector v1, v2, it transforms according to the following rule: m12, m11, sorry, m12, m21, m22, v1, v2. Where this is a coordinate transformation matrix, we consider only linear transformations in flat space, and most frequently we actually consider rotations, and this matrix is just famously known cosine phi minus sine phi, cosine phi. So this is just a matrix of rotation on angle phi. So this is a two-dimensional vector. But what is the difference? In tensor notations, vector is represented as follows. It's some quantity which carries index a, and a is ranging from 1 to 2. Then in tensor notations, this equality is written as follows. It's VA bar is equal to MAB VB. So in tensor notations, if there is a repeated index, it assumes that there is a summation. So this is literally means that there is a sum over b from 1 to 2, m, a, b, v, b. And let us see that this equality is actually this one. So explicitly, this is just two equations for each value of a. So we have v1, which is just m1, b, v, b, which is just m1, 1, v1 plus m12, v2. And similarly for v2 bar, m2b, vb, and so forth, obviously. So this is actually the same equality as this one. So this equality in tensor notations has the same meaning as this one. So what means tensor? Tensor is a quantity which carries indices. So for example, n tensor is a quantity which has n indices, a1, an. Well, I do not, I restrict myself to the tensor which carries only lower indices. You will see the difference between lower and higher and upper index tensors a bit later. So tensor is some quantity which carries indices, similarly to the vector, but there can be many indices. So tensor quantity is some collection of quantities which transform under rotations, under coordinate transformations as follows. It's m a1 b1, m a n bn times t b1 bn. So on each index among the n indices, there is an action of this, the same matrix. So this is called rank n tensor. Rank n tensor. Okay, so the simplest example of a tensor with two indices is just a tensor product of two vectors, for example, VA and double VB. This is a tensor with two indices. In fact, it carries two indices, and then the rotations transformed according to this rule. Each of these two vectors transforms with this matrix, so the rule is the same. So, in principle, if you have a tensor with two indices, it is convenient to place it in a matrix. For example, T11, T12, T22, 2, 1, T, 2, 2. But if you have a tensor with more indices, its placement into a matrix is already kind of cumbersome. In fact, well, in principle, we can place it in a matrix, cubic matrix of the following form: T1, 1, 1, T1, 1, 2. T1, 2, 1, T1, 2, 2. And then there is a second layer, T2, 1, 1, T2, 1, 2, and etc. So, but who needs this placement? This is, in fact, if you have tensor with many indices, you can place it in a hypercubic lattice, hypercubic matrix, but there is no point of doing that. So even this placement is pointless, because one has to get rid of this way of notations. One has to use tensor notations because they are convenient for many reasons, and we will explain why during this discussion. To clarify why we need tensors, let me introduce the notion of scalar product or norm in the space of vectors. So we all know that if we have two vectors, we can multiply them into scalar product, which is just V1 double V1 plus V2 double V2. Let me just stress why I use upper and lower index. In this case, it's like, in a sense, meaningless, but just to stress that we have something like V1, V2 multiplying double V1, double V1, double V2. And for the row, we use lower index. For column, we use upper index. So this is equivalent to this one. Now, in tensor notations, then scalar product can be written like this. Can be written like this, where we assume summation over A. So this is a scalar product of two guys. This is the same. How do we map lowercase and uppercase indices? Well, for that we use metric tensor. Bilinear form, which specifies the norm. For example, the norm of a vector v, so a scalar product of v on itself, can be written like this. It can be written like this or like this, delta AB, VA, VB, where how do we obtain lowercase from upper? So if we have a lowercase index vector, we can multiply it to a tensor with upper indices, delta AB. Who is this? I will explain in a moment. Then we obtain an uppercase index, and if we have uppercase index, we multiply it to this BA, and we obtain VA. So this is inverse of this, which is in our case is trivial. Delta AB times delta BC is delta AC. So this is just tautologically written thing. What is delta AB? Delta AB is just a unit matrix. If we write the matrix of this tensor, it's a unit matrix. Delta BC is just inverse of a unit matrix, so its matrix also is unit. We'll encounter a bit different situation in a moment later, but just so its matrix is also like this, and delta AC is just also, it's a Kronecker symbol, so it's a unit matrix. So using these things, we can map lowercase and uppercase indices to each other. So that's the reason we need them. And hence this can be written in many different ways. So it can be written like this, VA, VB, and etc. VB, VB. So these are different ways of writing the same things. And it means the same, literally this. And notice that due to these relations, the map between upper and lowercase indices is trivial. So if we have a VA, so its components are V1, V2, and we have vector VA, its components are V1 and V2. Due to these relations, one can observe that V1 is just equal to V1, and V2 is just equal to V2. So the difference between upper and lowercase indices in this case is tautological. And we just keep it to stress that this transforms as a column, this transforms as an arrow. So it means that this transforms according to matrix M, while this transforms according to an inverse matrix of M. And inverse matrix of M, in case of rotation, is just a transposed matrix. So this is what concerns with the tensors. And now one can see the reason why tensors are convenient. For example, suppose we have a tensor like this, A, B, C, D, E, F, G, like this. So we have a tensor with many indices. The order of indices is important because the tensor doesn't have to be symmetric. Some of the indices are uppercase, some of them are lowercase. And then we can take a product of this tensor to a different tensor, say with the letter B, which has index G, which has index A, like this D, for example, B, like this. So this product of tensors carries, as one can see, this index is contracted, so we have a summation over this index. This index is contracted, we have a summation of this index. This index also contracted, and this index is contracted. So the result of this is some tensor which carries 3 indices. So because transformation of this index compensated with this index and etc., we have something which transforms according to the rule how tensor with 3 indices is transformed. So we have in tensor notations, all the transformation properties under rotations are obvious. That's one of the reasons why tensors are convenient. Well, another option is just if we have tensor with 2 indices TAB, we can multiply it to VA double VB, and this will be a scalar quantity which doesn't have any indices. So this is another example of similar situation. And what else? And so using these things, we can lower and higher indices. For example, if we have a tensor like this, we can multiply it by a matrix tensor, by a metric tensor, and the result will be a tensor with 3 lower indices. And similarly, we can hire, for example, TABC, we can multiply delta BD. This will be a tensor with indices A, D, C. So these are the ways we can map lower and uppercase indices to each other. Perhaps we need to clarify further our notations. Namely, we have a tensor like this. It transforms according to the rule as follows, that there is M, A, C, and M, B, D, T, C, D. And what is the difference between this and this matrix? Is the one is the inverse of the other, namely if we have M, A, B, M, B, C. This is delta A, C. And what does it mean that we have an invariant expression? It means that if we have a quantity like this, for example, T, A, B, V, B, then we have the following transformation rule for this quantity, that this barred quantity is just M, A, C, T, bar, C, B, V, bar, without bar, sorry, V, B. So why do we have this relation? Because according to this and this rule, the transformation of this index compensate transformation this and this transformation of this index compensates this. And we have only one M gone out, and which states that this quantity transforms as a vector with one index. So, and all the rest follows. And several things are in order. So we have a metric. It means that if we have in our space 2 points, x and nearby points, x and x plus dx, or in tensor notations, xa and xa plus dxa. And then we can define distance between these 2 points according to the formula like this. dl squared is just dxa, or the same as delta AB dxa dxb, and the same as delta AB dxa dxb. So this is the same thing, and as you know, this is just dx1 squared plus dx2 squared. So finally, we should stress that because, as we all know, under rotations, this bilinear form doesn't change. It means that after rotation, we have that dxa bar is equal to dxa dxa. Namely, this is equal to dx1 bar squared plus dx2 bar squared, and this is equal to dx1 squared plus dx2 squared. So under rotations, the bilinear form doesn't change. It means that delta AB, which is a metric tensor, so it's a quantity which transforms according to the rule as tensors should transform, MAC, MAD, delta CD, but the components of the barred tensor coincide with the original component. So the matrix of this guy is the same as the matrix of this guy. This is not the case for an arbitrary tensor with 2 indices or with many indices. So this statement just means that we have invariant tensor. Another invariant tensor in 2 dimensions is totally antisymmetric tensor. Epsilon AB is invariant. In fact, it has this property, A, B, A, so it's antisymmetric. And if we specify that epsilon 1, 2 is 1, then one can obviously from these properties find that epsilon 1, 1 is 0, and epsilon 2, 2 is also 0, because under antisymmetry and the exchange of indices, it changes the sign, but it is equal to itself. So it's 0, and epsilon 2, 1 is just minus 1. So why is it invariant tensor? It's just because if we have 2 vectors, VA and double VB, the corresponding quantity epsilon AB, VA, VB, double VB, is nothing but the area of this parallelogram. And the area of the parallelogram after rotation, not only the area doesn't change, but even the formula expressing it after rotation doesn't change. So it means that this tensor is invariant under rotations. Similarly, in three dimensions, we have antisymmetric tensor epsilon I, j, k, where I, j, and k run from 1 to 3. And this tensor, antisymmetric under exchange of any two indices, it's two indices, so it's minus, for example, under the exchange of the first two indices, etc., etc. So it's uniquely fixed by its symmetry properties, and it's also invariant because epsilon I, j, k, vi, vj, wj, uk for three vectors which are not collinear, three non-collinear vectors in three dimensions. This guy specifies the volume of, how to say, this is not parallelepiped, but its faces are parallelograms. So I mean something analogous to parallelepiped. And so, the area for this parallelepiped doesn't change under rotation. The formula expressing the area doesn't change. So these are very similar today. In 4 dimensions, in 4-dimensional space-time, we also have epsilon, mu, nu, alpha, beta, which specifies antisymmetric tensor. What else should I say here about the tensors is the difference between space and space-time. And that I will clarify in a moment.